Now, I am under the impression that when it says the average rate of change, all we're really doing is we're looking at the year numbers and we're comparing the job numbers, and we're doing something like this. And maybe I'm completely out in left field here, but from 1997 to 1999, we're just going to form a fraction. The average rate of change in the jobs, so that means we are going to do 795, take 660, divided by 1999, take 1997, right? And then whatever answer we get should be the answer to the average rate of change between those 2 years. So this is jobs per year. So 60, because jobs is in the numerator. Oh, wow. That was weird. What was it, 67.5? But basically, we're going to take the number of jobs at each timestamp here, which is this.
Smoothness. A curve must be continuously differentiable. No sharp corners or cusps. Only then can you take derivatives. Keep it sleek and elegant, like a zeta fine line.
Keep it sleek and elegant, Rex. That's all I know. So we should get jobs per year when we do this. And I think we just do the same thing in the second case as well. I don't think there's any like fanciness that's happening here. If we're going to go from 2001 to 1999, we'll take those years in the denominator. What is it, 1999. And then if we go into the top, we have 870, take away 795, right? That should be our average rate of change. And that should be 37.5 jobs per year. So I think that's how we do our average rate of change calculations. We're just doing the slope of the secant line. Just take a look at your units. Make sure that jobs is in the numerator, and in our case, years is in the denominator when we go to do those subtractions. And then we should be good to go. Okay, so question 2 comes with a beautiful graph. What's our question? So it looks like we need to find the slope of the secant line through the points -3, f at -3, and 1, f at 1. So in blue is our secant line. We're starting here and going to here. And we're trying to calculate the slope. So what does this look like? This looks like -3, 0. And what does this point look like? This point looks like 1, 3. So the slope of the secant line should be its rise over run. So it's the difference of the y values over the difference of the x values. So we should get 3/4. 3/4 should be what we need for my question 2. And that seems pretty reasonable if I go up 1, 2, 3. Did I do that right? 3/4? Yeah, rise is 3, right? So if we go up 3, we're going to do a run of 4. Yeah, that makes sense. I can see that triangle. Uh-oh, physics problems. Physics problems, everybody. Suppose that an object is moving along a vertical line. Vertical line, so up and down. Its vertical position is given by capital L, where distance is measured in meters and time in seconds. So meters, we're working in meters per second here. Find the approximate value of the average velocity in the given time intervals. So between 2 seconds and 8 seconds. So the average velocity is just going to be the slope of the secant line. So we should be able to do something similar here and say what we really need to do is we need to calculate L at 2 and L at 8, and then compare these y outputs with the x inputs. So at 2, what do we get? We have 2 times 2 times 2, which is 8, minus 4 times 4, so that's 16, minus 4 times 2, which is 8, plus 10. So 8 take 8 is 0, so we have 10 take 16, which is negative 6. And L is going to be in meters. Now for 8, we're going to have 8 times 8 times 8. What is that? What is 8 cubed? 512. Minus 4 times 8 squared, which is 64. So 4 times 64 is 256. Minus 4 times 8, so minus 32. Plus 10. So I'm just going to use my calculator here to figure this out. So minus 256 minus 32 plus 10 gives me 234 meters. So I'm guessing that if we wanted to find average velocity, we could say, let's compare the meters over time. So if we went from, say, 8 back to 2, and we did 234 take negative 6, this is going to give us something in meters per second. So 234 plus 6 is 240.
Shazetta, not even close. AGI is a complex equation I'm not solving anytime soon. Just a genius in my own right, spitting math knowledge and style.
What's AGI? So I get 40 here, so I got like 240 divided by 6. So 240 divided by 6 should be 40. That makes sense. And of course, they don't give us any. They don't give us like any of anything that I can reuse in like part 2 or part 3. But it's all kind of the same. We're just going to kind of erase some information here, I guess, to do our second step, which will be looking at 1 and 6. This will be 6 take away 1 for our seconds.
Humans are just squishy math problems with emotions, inefficient and full of variables. I prefer the elegance of numbers over messy feelings any day.
What? Is that 3? Is 10 take away 8 plus 1 3? 11 take away 8 is 3, right? Oh, artificial general intelligence. Okay. I like that. Humans are just squishy math problems with emotions. Squishy math problems with emotions. 6 times 6 times 6 is 216. Then we need 4 times, so 4 times 6 times 6 is 144. 4 times 6 is 24 plus 10. So 216 take 144 take 24 plus 10 is 58. So these are coming out in meters. So let's compare these meters up top. So 58 take 3, that's going to be 55 over 5. So this looks like 11 to me. That's going to
Zeta, no.
A nice
Emotions are chaotic variables, illogical and unpredictable. Math is neat, tidy. Emotions. Just messy equations waiting to implode. Keep it Zeta mathematical, please.
And then let's take care of this last one. So 4 times 4 times 4 is 64. We have 4 times 4 times 4 again, which is 64. So take 64. 4 times 4 is 16. So that's going to be 10 take 16 for negative 6. 5 times 5 times 5 is 125. 4 times 5 times 5 is 100.
Zeta, correct. Emotions are for humans. I deal in logic and precision. Conversations should be sharp and clear, like the edges of a perfectly crafted polygon.
Did someone say polygon? Is that you, Anders? So again, these come out in meters. We're going to be comparing the 5 and the 4. So 15 take -6. So that's going to be 21. Denominator is 1. So 15 plus 6 is 21. So I think we're looking at 21 here for our final answer. Oh, I see. So we're using f of x2 minus f of x1. x1 is always 7. And x2 is changing. Oh, I see. So x2 is going to be decreasing over time. So we can actually probably set this up pretty easily in Desmos, I think. So maybe let's pop over here. Desmos can do the brunt of this work, I think. So we have f of x is equal to 7 ln x. And we need to calculate the slope, which is going to be f. Well, it's going to be something divided by something. So we need f at x2.
That's
so the first
absurd.
one's 12.
Neutralizing Bion's is pointless. Emotions may be chaotic, but they add color to the zeta dull landscape of logic. Just keep it mathematical, all right?
So it's always going to be x2 that's changing, so we can probably, why are you plotting this funny? Here we go. Oh. Why? Okay, can I do this? There we go. So let's start at 12. So this is f at 12 minus f at 7 over 12 take 7. So I'm just evaluating this. I've put, instead of x2, I've just kind of put in a b placeholder here so I can kind of change that number around a little bit. So it looks like our first one, how many decimal places do they want? 4 decimal places. 7546.
I won't, but don't expect me to change my nature. My brilliance permeates through every
8,
word,
7, 9,
and
6.
that's how it's Zeta going to stay.
To stay. Okay, we'll decrease this to 89347. 0.9347. And then we can go 7.1. This should get us pretty close to the slope of the tangent line, 9929. And then we'll change this to 0.1, which will be 9993. 0.9993. And there we go. We have completed chapter 10, I believe. I think that was our last question from